Okay, welcome to the first video about making questions for the PrairieLearn platform. This first video is just going to be focused on using Python to solve physics problems and also to randomize some of the variables so that each student can be presented with a unique version of the same problem. So I went ahead and I picked a random problem from the OpenStax University Physics textbook. So this is volume 2 of the book, and this is a problem from chapter 12, and it's number 55. And so I've pasted the text of the problem here. A solenoid with 25 turns per centimeter carries a current I. An electron moves within the solenoid in a circle that has a radius of 2 centimeters, and the circle is perpendicular to the axis of the solenoid. If the speed of the electron is 200,000 meters per second, what is the current? Okay, so first, before we get into any of the Python stuff, let's just solve this problem. So we have to recall a couple of things. Let's imagine that this is our solenoid. And so there's some windings around this cylindrical former. Okay, and maybe our wire comes out here. And so we have current I flowing through these windings. Okay, so the first thing that we're going to need to know is the strength of the magnetic field inside the center of the solenoid. And recall that B is mu naught times little n, where little n is the number of turns per unit length, so it has units of inverse length, and then times I. So if we take an end view of the solenoid, we're looking into the solenoid here, and so maybe what we have is our current windings are going around in this direction. And so if that was the case, by the right-hand rule, we would have a magnetic field that is pointing into the page. And so we have a magnetic field that points into the page. And then we've got inside here an electron in circular motion. And so let's imagine our electron is here. It has charge Q is minus E. And let's see, if we do V cross B, V cross B. So I believe what we have to have is our electron moving with speed V here. So if you did the right-hand rule, V cross B, that would be that would give you a direction pointing out, radially out from the circular motion, but because the charge is negative, the resulting force will be towards the center, which is what we're going to want. Okay, so the force on a charge moving in a magnetic field is V cross B times Q. The velocity and magnetic field are perpendicular to one another, so the cross product just ends up being V times B, and the magnitude of this force is QVB. And like I said, if you do the right-hand rule, I think you should get a force that points towards the center of the circular motion. Because the electron is in circular motion, it's undergoing centripetal acceleration, and the force must also be equal to the mass times the centripetal acceleration, which is v squared over r, where r is the radius of the circular motion. So if this is the center of the circle, then r is that radius. Okay, and so all we need to do is combine all of these results. So we'll take these two forces and equate them to one another. QVB is mv squared over r. We can cancel one factor of v. And we could substitute in our expression for the magnetic field, so that we have Q times mu naught times the number of turns per unit length times I that's QB is M V over R. And what we're trying to isolate, what we're trying to solve for, is the current I. And so if we solve for I, we get I is equal to, let's see, M times V over, let's write it, mu naught N times Q times R. And I think that should be our final answer. So what we're going to do is we're going to switch over to a web browser where we can write some Python code, and I'll show you how to do that. Before we do that switch, let's just think briefly about some of the things that we might be able to randomize in this problem. So the first thing we have is the number of turns per unit length. We have the radius of the circular motion, and we have the speed with which the electron is moving. And so all three of those things can be randomized, and all three of those are going to affect, so there's the number of turns per unit length, the radius of the motion, and the speed with which the electron is moving. If we have our charged particle being an electron, the mass and the charge are fixed. However, we could also imagine modifying this problem so that we had, say, instead of electron, maybe what we could do is we could randomize that. We could say an electron or a proton or an alpha particle. And if we did that, then the mass and charge would always change. So the mass of an electron and a proton and an alpha particle are different. The electron and the proton have the same magnitude of charge, opposite sign. Alpha particle has twice the charge, being a helium nucleus. So those are some things just to keep in mind. If you did randomize that part of the problem, then every time it says electron, you'd have to change the text of the problem to be, say, always a proton or always an alpha particle or whatever the case is. Okay, so with that, I'm going to stop this video and we'll transition to a new screen.